A stationary state is called stationary because in all observable ways, the system remains in the same state as time elapses. These states have a probability density that is independent of time, evolve in time with e to the minus iet over h bar for e the energy of the state, and are eigenstates of the energy operator, meaning they have a definite energy, E. But this is only a special class of states. By the superposition principle, in general, any linear combination of stationary states is a possible physical state for the system. Consider the following problem. Consider a particle in an infinite square well described initially by a wave that is a superposition of the ground and first excited states of the well. A, find psi of x and t at any later time t. B, what is the average energy in this state? C, what is the average particle position? We're given a normalized wave function that is a superposition of the stationary states psi1 and psi2, which I've written here. We know that psi1 and psi2 individually evolve with time according to their respective e to the minus iet over h bar factors. So the time evolution of their superposition, psi of x and t, is just going to be given by the evolution of each of these individual states. So here, psi1 of x gains a factor of e to the minus I e1t over h bar, where e1 is the ground state energy of the well. And psi2, the spatial wave function psi2 of x of the first excited state, gains a factor of e to the minus I e2 t over h bar. And this answers part A. This is the time evolution of their superposition. Now, for part B, we need to compute the average energy in this state. And that's given by the following expectation value, psi star, integral over psi star x and t of times e hat acting on psi of x and t. And this integral is over all space. So when the energy operator E hat acts on psi, well, it first acts on, let's write that. So when E hat acts on psi, it first acts on this stationary state, and then acts on this stationary state. And when E hat acts on a stationary state, that state just gains a factor of its energy, since stationary states have definite energies. So this term will gain a factor of E1, and this term will gain a factor of E2. But importantly, no factor of energy pulls out of this expression. E1 and E2 are different, and so E hat acting on our superposition does not equal some energy times our superposition. In other words, our superposition state does not have a definite energy. It is not a stationary state. Okay, so this is what E hat psi is, and that enters into the integrand here. And so we'll compute this expression is going to have, if I expand out this whole integrand, a term E1 integral psi1 of x squared dx plus the same thing with E2 and psi2, plus it's going to have a term proportional to the integral over psi1 of x psi2 of x dx. These integrals are over all of space. And this is because our spatial wave functions are real, and so this complex conjugation only affects these factors of e to the minus I et over h bar. So we're going to end up with two factors that go like psi1, psi2. Now, this is just because psi1 of x and psi2 of x are normalized, the integral over all space of their associated probability densities is just 1. So this integral is 1, and similarly this integral is also 1. This integral will give 0. And that's because the two stationary states with different quantum numbers, n1 and n2, are orthogonal. And you can show this explicitly, which I do in the attached PDF by plugging in with the signs and integrating over sine pi x over L times sine 2 pi x over L. The conclusion that you'll find at the end of the day, simplifying, is that the average energy in this superposition is E1 plus E2 over 2. So the average energy of our state is actually literally the average of the energies of the stationary states of which it's composed. All right, so now on to part C, where we want to compute the expectation value of x in this stationary state, which of course is just given by the integral over all space of x times the associated probability density psi of x and t squared. Okay, so this integral, when I expand out this probability density, we're going to get several terms. One of them is going to go like the integral of x times the probability density of the ground state. And then similarly, we'll get exactly the same term, but for the first excited state. These are coming from the modulus squared of this term and the square of this term individually. And these integrals we know how to do because we know what the average value of x is in the ground state of the well and the first excited states of the well. For any stationary state of the well, the average value of x, the position of the particle, is just L over 2, because their probability distributions are symmetric about the midpoint of the well. So we already know that answer. The other integral that is going to appear, the other type of integral that will appear in this expression, will go like x times psi 1x psi 2x. And so this one's a little more complicated, and I go through step by step how to do the integral via integration by parts in the attached PDF. What we're going to find at the end of the day is that the average value of x in this superposition is L over 2, and that's coming from these terms, minus 16L over 9 pi squared cosine omega t. This is coming from these terms, and the cosine is coming from an e to the plus I omega t plus e to the minus I omega t. I've defined the constant omega equal to E2 minus E1 over h bar. So the main point is that the average position of our particle in the well is not constant. It actually changes with time. It oscillates back and forth with a frequency of omega, E2 minus E1 over h bar, and with a period of t equals 2 pi over omega. I've collected our results over here. Over here I've plotted the probability distribution as a function of time. It sloshes back and forth with period t equals 2 pi over omega that we computed in this problem. The most probable place the electron will be found, or the location of the highest peak on this plot, goes back and forth with this period. This is pretty different than the case of a stationary state in the well, where the average value of the position would just be L over 2 for all time. It sloshes back and forth with period t equals 2 pi over omega that we computed in this problem. The most probable place the